Thank you very much. I'm very proud to receive the Harvey Prize as well. I guess this is my third trip to Israel and the first time to the Technion. So I'm very impressed with the Technion and what's all the things I've seen over the few days I've been here. I often start my talk out with a picture of the building in which the research is done, because I think it's a beautiful location, so I thought I would share it with you also to start out. This is the National Research Council building. This is the first science building built for the National Research Council. It was built in 1929. Canada is a young country. There was very little science in Canada before that. There was some, but not very much. It's on a gorgeous location. You can see the Ottawa River behind. It's a big river. And off to the left is the home of the first Prime Minister of Canada, Sir John A. Macdonald. It was a private home at that time, and eventually it was bought by the British, and so it's a home of the British High Commissioner now. Two buildings further, well, right beside it is another small river with a mini Niagara Falls flowing into the Ottawa River, and just beyond that, by two buildings, is the Prime Minister's residence. So it's a lovely location, and if you wish to come and visit, it's a good place to come. Laboratories are down here in the bottom and all along this end. Now, if you were to look at it now, it wouldn't look like this. It's getting better, but it'd still be probably quite a bit of snow. This was taken obviously in the fall, in October. So I'll show you a picture that was taken from my backyard just before I left, just on the Sunday before I left. I left on a Thursday, and we had snow on Sunday. Actually, this is not quite true. This was taken 2 weeks ago when it started to get warm. You see a squirrel up on my roof, and he was looking for, well, seeds that fell in the rain gutter in the fall. He was happy to find the snow starting to recede, and he could get some seeds, and he made quite a mess. However, it snowed the next weekend, and all the trees are laden with snow. It's very beautiful. But kind of discouraging at this time of year to see so much snow. I wanted to take this. This is our barbecue table, or not barbecue, our table, picnic table that's out in the backyard. So it gives you a measure of how deep the snow, because you know how big a table is. And the snow depth is approximately the depth of the table. However, ever since I left, it's been warm. Today it's supposed to be 14 degrees, and so snow goes pretty fast at 14 degrees. So I'm hopeful that when I go back, it'll be gone. Anyway, I thought you might think it's unusual to see such snow. Okay, I thought I would try to do two things. I understood this was a specialized seminar, and so I wanted to talk about Attosecond technology, and I'm going to talk about generation. I'll give the background that I've given before, just in case people are from outside, so you are brought up to speed on the background, but I won't spend too long on it. And I want to talk then about generating attosecond pulses, and I want to pick an experiment we did over the last year approximately, in which we introduced to gases an idea that has been developed for solids just slightly before that, of what we call photonic streaking, or that could otherwise be called the attosecond lighthouse. So I'll talk about that, and then I'll go on and talk about how you can make measurements of attosecond pulses. And I use the gold standard, what I call the gold standard of attosecond pulse measurement, which is the attosecond streak camera, and I'll introduce the ideas of that. Then I will go on and work on the quantum mechanical. I'll give the introduction all at once to both the classical and quantum mechanical part. And then I'll talk about how you can do space-time measurements of attosecond pulses as they're being formed, full space-time reconstruction of an attosecond pulse. I think it's interesting. It's a very interesting and unusual way to make the measurements, and this is research we've done in the last year or so in Ottawa. And then finally, I'll talk about, I misspelled that, an all-optical attosecond, a petahertz oscilloscope. Okay, so by way of background. So a lot of attosecond science can be understood very, very, very simply with just F equals ma. And if I have a class of students which are not here, I always tell them this is the only one you have to understand, this view graph. And anything else, if you let your mind wander, just remember this view graph and you will get it. You'll be able to catch back up again. Because it gives you an intuitive sense of how attosecond pulses are formed. I will give you an intuitive quantum mechanical sense just only a few view graphs forward. And that also is not so complicated, but maybe for a first-year student it would be, but for a senior student it would not be. Okay, so the first-year student, even high school student version, which you can understand almost everything from, is shown here. A light pulse shown in yellow, a light field, I should say, shown in yellow over one cycle, irradiates an atom, or truly a gas of atoms, with sufficient intensity that it's ready to ionize the atom. So that's what's shown here. Here it's shown for a 2-electron atom, but largely I'll only worry about one. The electron is at some field classically free. Quantum mechanically, the electron would tunnel. Classically, you could think of it going free. And it will go free somewhere near the peak of the field. Tunneling, of course, explicitly will occur over a set of phases, but classical physics really would too in a three-dimensional problem, because the electron has to find the hole to get out. So the electron is ionized somewhere near the peak of the field, and once it's ionized, well, let me say what those fields are. The field that's required to ionize a typical atom, a rare gas atom, xenon, krypton, argon, helium, or something like that, varies between a few times 10 to the 13 in the case of xenon, up to about 10 to the 15 in the case of helium. This is ionizing in an infrared field, so many photons involved. And you would calculate that directly from a tunneling-like calculation. Okay, so that means that the fields that are pulling on this electron, once it gets more or less free from the atom, are on the order of a few volts to 10 volts per angstrom. These are non-subtle fields. The electron will respond to them even over the time scale of the field oscillation of an infrared field. We will largely be working about 800 nanometers, so the periods are about 2.7 femtoseconds. So over femtoseconds, the electron will move. I knew that might come up again.
Change remind me to like 40 minutes.
Yes, that's exactly right. 1 hour, it's even better. Okay, so that's so the electron gains momentum, and if you wish to think about why classical physics works, it will gain momentum in these kind of fields of tens or hundreds of electron volts. So many, many photons, and often classical physics is good for many photon process, something like this. It gains momentum and moves significantly away from the atom. It depends on the period, how far it will go, because the force acts for longer. At 800 nanometers, it will go in the order of a few tens of angstroms. And by then, it's got momentum, so it works against the field, but it can be driven back and recollide. Now, those electrons, you can do F equals ma in your head, everybody in this room. If it's born here, it's accelerated away until the zero crossing, getting lots of momentum, comes to rest at the equivalent place here, and it never really comes back again. The kinetics would be like this. The electron goes away. But if it's born after the peak of the field, and somewhere in this region out here, it goes out but not so far, and it's driven back and it recollides. And that's what's illustrated in this illustration. And you can see it coming in and knocking another free, which occurs. An E2E scattering, or non-sequential double ionization, as it's called in the field. However, that's not the only thing the electron can do. The electron can elastically scatter, of course. And elastic scattering is not illustrated here, but elastic scattering, if this were a molecule, is simply diffraction. So it can diffract from the molecule or elastically scatter from the molecule. But what's of interest here is the electron can recombine to the state from which it came. Recombine, giving out the kinetic energy of the electron plus IP as a photon energy, an event that may seem unlikely, but it will phase match for many atoms. Now, depending on the moment of ionization, if it's ionized late in the cycle, F equals ma brings it back rather early and with low kinetic energy. If it's ionized a little earlier, F equals ma brings it back a little later with a little more energy. And if it's ionized at the optimum time, which turns out to be about 17 degrees here, it comes back with the maximum kinetic energy. And I've simply put numbers on here arbitrarily because it depends on the field strength and the wavelength what those numbers are. But you see immediately that there's a large range of kinetic energies, and so lots of possible photon energies for making very short pulses. And you can see that the time of recollision, or the spectral phase, is well synchronized between all the colors. And that's therefore important for the generation of a very short pulse. So we have all the ingredients for making a short pulse. In fact, this will occur over only a fraction of a cycle, and so that itself, although it would be chirped, would be an attosecond pulse as I described it. Now, if you're thinking about it, you might say, well, there's going to be electrons colliding over this next part that you didn't show and you're ignoring, and they're electrons that are born between 17 degrees and 0 degrees. If the ion plays a big role, maybe a little more phase. And they do contribute to recollisions here of lowering energy as I go later in phase. But there's a divergence that can take them out of the problem, and largely we don't have to look at them. So I'm going to ignore them for the rest of the talk. But if you wish, I can talk about them later. So this is attosecond pulses. There's the attosecond pulse right there. And to make the state-of-the-art attosecond pulse, the only thing you do is do something to get the phases synced up, put it through a dispersive material. That's the only thing that's been done beyond this. And you understand everything about that attosecond pulse just about from this F equals ma picture. Now, here and in my talk, you may occasionally hear me talk about high harmonic generation. And I want to make the link between high harmonic generation and attosecond pulses, because high harmonics are also important. High harmonics, so the process I described to you is ionization, recollision, giving a burst of radiation. But if the pulse is longer than a single cycle, it can happen more than once. Ionization, recollision, a burst of radiation, and therefore you get a train of attosecond pulses. A train of attosecond pulses, Fourier transformed with a grating, gives you a set of harmonics. And if this is a symmetric system, this is shown for an asymmetric system, but if this were a symmetric system, these would only be odd harmonics. The electron is coming once this way, and once this way, and then that way, and then that way, flipping phase of the dipole every half cycle. And Fourier transform, that's odd harmonics. If the system doesn't have inversion symmetry, they're even, and this experiment that I actually took this from shows even harmonics. That's an experimental result. So this gives you XUV radiation covering the spectral region that I sort of made up before 0 to 300 eV. In fact, it can go up to about a little over a kilovolt in a harmonic process from 800 nanometer or infrared light. I'm not going to spend a long time in the introduction, but I want to just emphasize, so I always put this in just to make sure I don't forget, emphasize that it's not a single atom process, it's a many atom process. I've only described the single atom behavior, but if you think about the many atoms, so first let me say why I'm free to talk about the single atom behavior. I start with an electron by ionization from some level. I return the electron by recombination to the same level. Just like all nonlinear processes, you come back to the same place you started, in cars or second harmonic generation. And same here, and that allows phase matching. That allows one atom and the second atom and the third atom and all the characteristics and where they lie to sort of cancel out of the problem. So that as I go, I create my attosecond pulse here in this atom, and I do exactly the same here, and the attosecond pulse before is phase matched to what I make atom by atom by atom. So it's a phase match process, and it's therefore, and it's very you have many of around here in the Technion. And so, and you do experiments here. There's experiments, very beautiful experiments here in the Technion of this sort. So you don't have to come to Ottawa to see it. You're welcome to come to Ottawa, but you don't have to come for this. So here's an example made from argon gas with an 800 nanometer source of a set of harmonics stretching from about 25 electron volts out to 50 in that case. Or if I engineer my pulse so there's only one recollision, here's radiation stretching from about 25 electron volts out to 100 or 125. I'll show you this and what it means. I didn't say anything about what's in this. This is a vertical direction on the spectrometer. This is the spatial profile in the vertical direction in the medium in which the attosecond pulse is formed. But you'll see this much more later on. Okay, so now you know how the pulses are made, you know how high harmonics come, and you know that it's not single atom, although single atom ideas are extremely useful as long as one keeps phase matching under control. There are a number of ways to ensure that you have only a single recollision. And I'm going to spend quite a bit of time a little later on to talk about one of them using space-time coupling. This will be the issues that I will talk about next after I give my introduction. But let me say quickly what those methods are, aside from this, which I'll come back to. So the first method by which attosecond pulses were made by simply controlling the time-dependent waveform of an infrared pulse, 800 nanometer. So something like this is potentially possible to be made, and a pulse like this leads to an isolated attosecond pulse. When the field is not very strong, the electron doesn't ionize or doesn't ionize well. When the field is quite strong, it ionizes well. The electron is driven back and recollides with high momentum, giving you a burst of radiation going to short wavelength light. If the ionization occurs here, the electron is pulled away, but driven back by a weak field and recollides weakly. So if you look through a filter, there can be only one burst of radiation, and that's the way that it was first done in Vienna and the way that the Krauss group, which moved from Vienna to Munich, does it in Munich. A second way is to use a pulse with time-dependent polarization. Now, I didn't describe to you, and I won't describe to you circularly polarized light any more than getting you to F equals ma in your mind. So first, think about what happens in circularly polarized light. Some field, the electron ionizes. It starts at rest. It gets accelerated in the field away from the atom. Let's assume that's vertical. But the field's changing its direction, so the electron is pulled off, and its F equals ma motion will be a spiral like this. It doesn't recollide. In fact, even until it's really pretty close to linear, it doesn't recollide. But you know this from conservation of angular momentum, that there's n units of angular momentum in the infrared photon, well, 1 unit in the infrared, and there can only be 1 in the harmonic. And if you're going to balance angular momentum, you could not get it until there's roughly an equal number of left and right circularly polarized photons in the beam. So it's possible to produce a pulse that starts circular, goes linear. I don't know if it's possible to understand this figure, but this is what it means, and goes back circular of the other polarization, just passively with wave plates. And so that's a more standard way of making an isolated attosecond pulse. Only during that brief interval of linear polarization in this longer pulse is it possible to get radiation in a burst, get a recollision. So it's called polarization gating, and it's using time-dependent polarization.
CEP.
Pardon?
CEP.
Oh, I'm sorry. Did I have CEP? I'll require CEP. Okay. Now, I didn't say that. I should have said it when I was here. I just didn't think about it. So I'm glad you asked. This will be true for all pulses, but it's easier to show here. I've chosen a phase of the oscillation inside what is there, an imaginary envelope, but you can certainly imagine it. There's no magic in that phase of the oscillation inside the envelope. It could be anything. If you allow the pulse to propagate even through ordinary air, there will be a difference between the group velocity, which is the envelope, and the phase velocity, which is the oscillation. And so this will evolve from there to something else. But my description to you really had the electron being formed at a particular pulse and recolliding and looking through a filter. So it was sensitive to this particular form of the waveform. That's called carrier envelope phase. The envelope is the envelope, but it's very short, so I can find out where the center is so well that I can lock the carrier to it. Now, it's not a unique characteristic of a pulse, but you can measure it and you can force it to be fixed. So that work started out in the work of Ted Hench and others and led to the 2005, I think it was, Nobel Prize for CEP, carrier envelope phase control for optical clocks. But it's been brought into our community, as Ted Hench understood it would be, into our community because of its critical nature for this. I always say it's awfully important if I take my hand and drive it this way and hit myself in the face, or take it that way, right? So equally true for all these recollision effects. So I'm sorry I didn't mention that. The third way that's brought into gating, or it's been proposed for gating, these are called gating techniques, using longer pulses to, this is polarization gating, this is two-color gating, is to bring two color fields together where the second color is second harmonic. And if it's phased as you see it here, then the two fields add at appropriate phase, and they cancel at appropriate phase. In one direction in space, there's a strong field. In the other direction in space, because of the superposition of the two, the field is weak. So tunneling only occurs every cycle instead of every half cycle. Therefore, recollision can occur only every cycle. And you slow it down from being every half cycle to every cycle. And that's an awfully big advantage, and it allows you again to relax the conditions on this pulse. So the third cases are to use space-time coupling, and I will come back to them a little later on. Okay, so I hope that everybody understands the essence. Everything is forcing a single recollision, except this, which is a slightly different approach. Now, I want to give you a quantum view of this as well. I think it's important to see it both, and it's awfully nice to see them side by side. So I said you can understand many, many, many things from the classical perspective, and everything I've told you here, and almost everything that's involved with measurement by streaking, the gold standard, can be understood classically. But there is a quantum perspective, and I think it's important to see it, so I want to say it. So, quantum mechanically, of course, everything's a wave. I still want to give a qualitative picture. Coulomb potential holding the electron in place. There's the electron. It's now a wave function. The electron tunnels through a barrier. Of course, it doesn't come out as a classical particle. It comes out as a wave packet into the continuum. Portions of that wave packet move in a classical-like manner. It's hard to draw that, and of course it would be a movie if I did, but I want to keep it clear. So I try to indicate it here with this wave going out, and I got this classical trajectory, but it's only portions that follow classical-like trajectories. The wave packet itself is doing its complicated thing, and portions of that wave packet are driven back to overlap the wave function from which it left. Two portions of the same wave function, one portion a wave packet in the continuum, one portion the wave function left behind in the atom. This is basically an interferometer, and I think to think of this as an interferometer is useful. So I want to stop before I go to the next part and concentrate on that interferometric-like nature of it. Tunneling is a beam splitter separating two portions of the same wave function in a perfectly coherent way. The phase here determines the phase of the wave packet that's created. So tunneling is a beam splitter. The electron moves over a trajectory, which we've already talked about. It depends on the field strength and it depends on the wavelength, but typically it will be tens of angstroms. If the wavelength is very long, it could be considerably more. The motion out here is that oscillation motion, more or less. There's a way to try to deal with this, and that is consider it a Volkoff state, and that's what's often done in the strong field approximation. So strong field approximation. And the electron is driven back to overlap or to interfere, two portions of the same wave packet overlapping each other. So in other words, we've created an interferometer of the molecules or an atom's own electrons. It's a sheared interferometer in the sense that the wave function here and the wave packet here have very different kinetic energies and things like that. In fact, it's an interferometer in which we have tremendous control, and I'm going to use that control in a great deal of what I talk about the rest of it. I like to stop at this point and say, I think everybody here is an optics person, that everybody has an optics background. I like to stop at this point and say, think about this from an optics point of view. We use interferometers for all kinds of things in optics. I'm a short pulse person. We measure the pulse duration only with nonlinear optical techniques, nonlinear interferometers. Measure E as a function of T with an autocorrelator, which is shown here and which is there in that illustration, but perhaps I will assume everybody knows an autocorrelator, and I won't describe an autocorrelator. But we use it to measure pulse durations in frog, autocorrelator, spider, all the funny names we give to pulse duration measurement techniques. We don't so often in optics use the interferometer because there are other ways to do spatial measurements, but we could, should we choose to. We could measure E as a function of X with a sheared interferometer. For example, we could bring two beams in and look at the interference. So, I think it's therefore natural to say, is it possible to measure the attosecond pulse as it's being formed in this recollision, since it's being formed in an interferometric-like process? As it's being formed, I'm going to try to show you that it is. And is it possible to measure the wave function from which it originated in this kind of measurement, and that I talked about on Tuesday or Monday, I believe it was. So I won't talk about that. So I want you to, that's all part, this is just the quantum mechanical version of F equals ma. So you're going to say, okay, but with my interferometer, I know how to look at an optical interferometer and measure the interference fringes. How do you measure the interferometer that's this electron interferometer that we created with light? Well, we measure it through the radiation that's created. And so this is a way of looking at that measurement. Here is the recollision electron coming back. It's shown now as a 2D. Of course, it's overlapping. It's a 3D thing. I want to show it as 2D. The wave function, you can imagine the Gaussian that was in this illustration before. And this has caught the moment of overlap at some moment of overlap, and we've just simply added wave functions there. So you can see where there's a minimum overlapping that we have a minimum, we've subtracted, and where there's a maximum overlapping we've added. And so that corresponds to, when you square it, having the charge preferentially on one side because of this interference of the system. So we're calculating essentially the dipole, and it's the dipole oscillation or dipole acceleration that gives us radiation. As the wave function, as the recollision electron moves forward, that interference moves from one side to the other side of the atom, and that electron is moving very rapidly, so that motion is very fast, and so there's this fast oscillation. In fact, that fast oscillation determines the frequency, which is the kinetic energy plus IP is returned to the light as photon energy. So that's what determines it. And this is the oscillating dipole, and you see the oscillating dipole. Let me just comment that the electron that underlies this process, so the wavelength that I'm talking about here of the electron, the electron that underlies this process is all on the order of, well, I said from 0.1 angstroms to 3 angstroms. 0.1 angstroms is quite a high kinetic energy electron, but high kinetic energy electrons are allowed in this problem. So it's important, it's on the size of interesting molecular or atomic structures. So it gives us potential for imaging in this area of science because of that recollision electron. And that recollision electron information is transferred to the light. So actually, inside the light that we're going to see as the attosecond pulse is information on structure if we have something of structural interest to look at. Important for attosecond pulses or high harmonics is that the amplitude and phase of the recollision electron is transferred to the light through this dipole moment. Actually, if I wrote down the dipole moment, which I took out, but I didn't take out this, I'm sorry. If I wrote down the dipole moment, you could even see that actually physical structure of the interference or the orbital structure is somewhat encoded in this. Actually, it's interesting to say that of course, the photons that are created have a longer wavelength than the electrons, but the electrons are playing a big role in this. Okay, so I'm now more or less finished this part?
Yeah, I have
yes.
a question about this picture.
Yes.
So this is like a semi-classical way of...
Yeah, it's a semi-classical way.
You didn't say anything about the recombination of the electron, right?
In a way, this is the recombination of the electron. The dipole that is induced is really the transition moment. I just took it out with the figure. So this is the transition moment. The dipole, the radiating dipole is a transition. These are just two different languages for saying, I'd like to see it as the dipole because you really, in this picture, you see the electron moving back and forth. You understand where the phase comes from in the problem. And so that's why I like to, but it's the transition moment, it's the same thing. Is that okay? Okay. I argue that this is an interferometer. And so let me stop for a second and comment on this interferometer. We have control over this electron interferometer, as good control as we have over any optical interferometer you can think of. Okay, so how could you possibly do it? Well, one way you could imagine doing it is to change the length of the arm here, and one way would be to increase the light intensity, increase the field, the electron goes over a slightly different trajectory. That's sort of an inelegant way to do it because you might have fluctuations in your laser and it's not so easy to see. A better way, or a more interesting way, is to bring in a second color. We frequently use second harmonic, and there's a lot of work being done here and in the Weizmann Institute, so in Israel, using second harmonic. And one way to think about it is second harmonic is taking this interferometer arm, and depending on the phase, it's adding or subtracting a little bit of energy, a little bit of trajectory, therefore a little bit of phase. And just like a micrometer in a real interferometer, we change the length of this light-generated interferometer in a completely controlled way by the amplitude and phase of a second color. But there's no reason why we can't make the second color come in from another direction. And again, that's been used very effectively here to make circularly polarized light here in the Technion. So we have great control over this interferometer and the main arm on the interferometer. But it's not the only way we can control it. We can control it by putting more complicated things in an atom here, or maybe exciting a couple of states here, and that is in some sense controlling an arm of the interferometer as well. So in Ottawa, we do experiments by taking molecules and aligning them up, and we can change the alignment of the molecule, for example, or we excite a molecule and allow it to go through a complicated chemical process, and we can see, and that in a sense is moving an arm of an interferometer. Okay, so that's sort of the introduction. Now I want to talk about an experiment in which we've done, which I called photonic streaking, or that can be called the Attosecond lighthouse. We did this experiment with the group in France, CEA, the group of Fabien Carré, so I'd like to start out with that. And the idea comes from sort of Fabien Carré thinking about what would happen if we had a space-time coupled pulse. But it was indirectly influenced by this two-color idea that I just described to you before. And the reason I became involved in it is I started arguing to him about the two-color possibilities, and he argues that stimulated his thoughts. So we go to a lot of trouble in short pulse science to make sure there is no space-time coupling on our pulse. We want our pulse to be exactly the same all the way across its spatial profile as we look at it in time. The time should be the same on all sides. But Fabien Carré began to say, what would happen if we had a pulse who had a space-time coupling on it? What would happen if we preferentially, not so much as I show you here in a ray diagram, put the blue on the top and the red on the bottom? I like to start with this. I like to say, here we have the blue on the top, there it is, and we have the red on the bottom with much longer wavelength, there it is. Think what the wavefronts look like in that pulse. There would be the wavefront. I just connect the peaks to peak. The wavefront rotates as the pulse goes through from one cycle to the next cycle to the next cycle to the next cycle. So here is a space, vertical position, wavelength, frequency map of such a pulse in a calculation. And here's what you get if you think about what happens to the beam that's created in such a beam. Now let me just stop and mention what that means. Here we have ionization, recombination, and we tend to emit a beam in that direction, pointing slightly up, shown in the vertical part here. In the next cycle, ionization, recombination, and the beam tends to go forward, and we get that one, and the next cycle similarly, and the next cycle similarly. So we have a wavefront rotation on the fundamental beam, and that should lead to a rotation or a sequential attosecond pulses emitted in slightly different directions. So you can see that directionality. You can think of this as a streaking, or you can think of it as a vertical position, but time maps into the position in this case. So this experiment is what we're going to try to look for, and we're going to try to create exactly that kind of condition and in an experiment. Well, we do it. Here's the pulse that we create. It's an 800 nanometer pulse, approximately. You can see the full spectral content of the pulse. We take it through a two-wedge sequence that are just slightly unbalanced to allow just weak dispersion on the pulse. So the blue and the red are offset in the way we've described it. And here's a measurement made in the Fourier plane, or an image of the Fourier plane. There's the vertical position, and there's the wavelength of the pulse. You can see the modulation that you saw in the spectrum here on the pulse frequency here, and there's a motion from top to bottom. So the blue is on the top, and the red is on the bottom. And here is a calculation of what the wavefront rotation should look like in that experiment. So everything you see, early will be on the top, so that's the way we set it up, and late will be on the bottom. I didn't mean to make the movement, but there it is. So first, here is a harmonic spectrum that's created without any wavefront rotation. In other words, if we balance the wedges just perfectly, there's a harmonic spectrum from this experiment. And as we unbalance the prisms, then we see exactly what I described to you before. We see a set of 4 different beams. These beams are spatially separated, vertical position there, frequency here. This is done in neon gas with a 800 nanometer radiation, just exactly the data I showed you before. There's a set of 4 different beams all going in slightly different directions. There's a modulation between one and the next, or on each beam. That modulation is relatively weak. It corresponds to about a 1% overlap between one beam and the next. And we think that's the cause of the modulation. Of course, the depth of the modulation that we measure as we integrate over the frequency is not as deep, but there's a fluctuation in the carrier envelope phase that we think is responsible for that. I'll show you that in a moment. So the modulation, we think, is about 1% in this experiment, or the overlap is about 1% in this experiment. here's a movie of what happens as we change the carrier envelope phase. You can see the carrier envelope phase counting here, up there. So we can, that's under our control in an experiment by moving a wedge back and forth to add a little more ordinary regular dispersion. And we're relying on the difference between group and phase velocity dispersion. So this, you can see that we don't have perfect control over it. You can see it jumps around a little bit. And as I said, we think that's the cause of the less steep modulation in the actual integrated signal along the horizontal, along the frequency axis, than it is than along the other. Okay, so this is that data just plotted here. You can see each modulation moves as a function of the carrier envelope phase, so we have a modulation, and as the carrier envelope phase moves, it's moving its way down, as you see in the illustration. So that's just the measurement there of what we saw before. As we move the carrier envelope phase by pi over 2, we change the modulation position by, it's every half cycle, of course, you get radiation. So that's just exactly what you expect. There are many things on here. I probably won't spend so long on it. I actually lost track of the time I started, so I don't know, because I wasn't quite in control of it. I don't know how much time I have. But what time should I be thinking about? 15, 20 minutes? Okay. I just wanted to, I looked at my watch and I thought, do I go to, what time do we start? I couldn't remember. Okay, so there are many details here that you can look at that are interesting. The cutoff frequency is determined by, as you know from F equals ma now, by the kinetic energy that the electron recollides. That depends on the instantaneous field, and in such a short pulse as this, that will vary from cycle to cycle, and we see it varying from cycle to cycle. And it depends on the pulse we have, if it's a sine or cosine. So as we take it and move from this cosine pulse, where you see that the largest kinetic energy occurs, and you can just track where that should be, and so on, we see those changes. And we can change to the sine, and we see the cutoff change to 2 equal ones, and so on. I won't belabor these, because I think maybe these are very specialized to those people into recollision physics, but we see all the things that you expect to see in recollision physics. I don't want to leave you with this being obscure, but I'm not sure it's worth a lot of time. It's kind of specialized. So it's interesting to use this now in other ways. So instead of doing the experiment as we did before, this was all done on neon gas, but we only had enough energy to do neon gas and show you what we saw. We couldn't really drive neon gas very hard. We moved to nitrogen. Nitrogen has a much lower IP, and so the intensity we have in the problem can be used to ionize nitrogen as high as we want, well, fully ionized, or pretty close to fully ionized nitrogen. And so here's a sequence of 3 different figures taken at 3 different intensities in the process of creating these attosecond pulses. Now in nitrogen gas, the ionization potential is less, and so the lines are less well resolved, although I think you can see them there. The actual interference fringes changed. They actually changed on neon as well. I didn't show you that they changed, but they changed the neon as well. And these are the self-phase modulation ideas, similar ideas, that happen in high harmonic generation. It's not exactly self-phase modulation, but their frequency chirps could come in high harmonic generation. And these are those kind of frequency chirps, and you see them happening across the pulse at low intensity. As we increase the intensity, we begin to ionize nitrogen more, creating more background plasma. More background plasma makes it challenging to phase match, and we see 2 things. We see that harmonics now are generated earlier in the pulse, higher up in the time is coming from top to bottom, higher up. And we see that we begin to have problems with creating high harmonics here because phase matching is compromised. And as we increase the intensity even more, we have basically 2, and out here only 1 recollision. So this is probably a clean attosecond pulse that's created only gated by plasma. We haven't measured it directly. And so we can study this process of phase match destruction because of ionization. In principle, it could be depletion of the ground state, but I think if you look at the numbers, this is the destruction of phase matching. This tells you then that this is, we began to think of this as a streaking. So this gives us an ability to look at dynamics occurring in the medium, either ionization dynamics that's naturally occurring here, or other dynamics that we might excite in the medium, and we could then probe in this streaking-like manner through the photonic streaking. So that's the photonic streaking and one approach that I wanted to go through completely to making isolated attosecond pulses. So I think it's fair to say, well, I'm going to show you in a second, we generate single attosecond pulses using standard high harmonic setup, although the pulse can't just be really long. It has to be relatively short. More interestingly as well, we create 3 or 4 pulses, each going in a different way. And so we played a beam splitter. These are all phase-related pulses. And so we create a beam splitter for attosecond pulses that can be used in pump probe experiments and even in coherent pump probe experiments, I believe. We have access to individual attosecond pulses in the train. We have an all optical method for studying phase matching, and we can map physical processes that occur over multiple cycles, such as ionization gating with attosecond precision. So the underlying radiation that we used at 800 nanometers was created by a femtosecond laser, no different than what you have in the Technion. And I believe, but I'm not positive here, I don't know if I saw one, probably at the Technion also you can take and bring the beam into a hollow core fiber and compress the pulse by self-phase modulation, standard self-phase modulation that everybody I think in the audience will know from ordinary optics, self-phase modulation and compression in 1.8 microns down to the pulses that I showed you before. And we can go down to about a cycle and a half in practice in many places in the world. That process is equally valid at 1.4 microns or 1.8 microns. And in my laboratory, or in the laboratory in Montreal of a colleague of mine at the Advanced Laser Light Source in Montreal, they've developed this technique quite well at 1.8 microns, and we've transferred it to our laboratory as well. The person in Montreal that's done it is Francois Legary, if you know him. And at 1.4 microns, using SF10 glass, they've gone down to sub-3 cycle pulses. But much more interesting, at 1.8 microns, fused silica allows you to correct many orders of dispersion, just not ordinary linear dispersion, but the next order as well. And it's been possible to go down to 1.6 cycles of light at 1.8 microns. So we have brought that process, and so it's possible to do exactly the same kind of gating. I'm sorry for these images, these are rather new results, at 1.8 microns as well. So here's nitrogen gas, here's krypton gas, and here's xenon gas, all creating harmonics, photon energy along here, spatial position here. You know how to interpret them. You can even see the giant plasmon resonance in xenon. I don't know if you can see it back there or not, but there's the signal increasing from a minimum. And here in krypton, the signal decreases for the same reason, the giant plasmon resonance, and we don't show it increasing. I will show you, after I come to the issues of measurement, how that one of these pulses at 1.8 microns can be an attosecond pulse. So if I have 15 minutes to talk, I will go quickly through the attosecond streak camera, because this is not new work, this is old work. I wanted to bring people up to date on up to speed. I've told you about how we make attosecond pulses. I want to say briefly how we measure in most experiments attosecond pulses or attosecond phenomena, and then I want to go back to a new way. So I described how ionizing atoms, really ionizing atoms are incredibly nonlinear. That's really what the message is, isn't it? Ionizing atoms are incredibly nonlinear. So instead of have to measure an attosecond pulse, one approach is to use an ionizing atom. So let's bring my attosecond pulse in, ionize the atom. It's now an ionizing atom. If that's all that happens, out comes a photoelectron, just the opposite of what we did to create the attosecond pulse. It's photoionization in reverse, in a way, creating an electron of some energy, which is given by IP, h bar omega minus IP. And so there's the velocity of the electron, and I like to draw it as a circle because I don't know exactly what direction it will go in, so I'll allow it to go in any direction. But by creating this ionizing atom, I've made this incredibly nonlinear material. And a weak, not an incredibly weak, but a relatively weak infrared field can influence that ionizing atom because of this nonlinearity. Or just because of F equals ma, if you wish. All you have to do is F equals ma with an initial velocity, and you'll calculate everything about the streak cameras. No more complicated. Still a first-year student can do it. So think about the attosecond pulse in the presence of an infrared field. We've made it with the infrared field. It's perfectly phased with it, so we can phase the attosecond pulse anywhere we want in the infrared field. Just apply F equals ma with the electron with the initial velocity from the photon energy minus IP. And you find out that in the phase that I've shown you here in blue, the electron gets a boost pushed towards this direction. And the phase I show you there in red, the electron gets a boost pushed to the other direction. In the phase I showed you in black, the electron is oscillated but comes back to the same velocity when the pulse turns off. So we have a way of moving the electron velocity dramatically over what it would have been by just simply moving back and forth in the time-dependent field. Or actually, if you sat here, you would overlap with a short pulse a range of time-dependent fields. And this part would get a boost, and this part would get the opposite boost. And you would see a broadening of the spectrum, and that's sufficient to measure an attosecond pulse. And as a matter of fact, if you go all the way through this process, that is, you take all phases and you measure the spectrum in one direction, just put a detector out here, measure a spectrum in one direction, you have 2D information just like in a frog, and everything can be reconstructed from this 2D information. Experimentally, it's straightforward. A beam creates the attosecond pulse. The attosecond pulse is separated from the fundamental by a filter, a thin metal filter. A little visible is either taken around with a beam splitter from out here or allowed to leak beside it because of the divergence difference here. And both are focused simultaneously onto a second jet for measurement, and the photoelectron is measured in a certain direction. So exactly what I showed you. We choose a direction. We look at the kinetic energy. And this is what happens if you have a in this case, it was a 70 attosecond pulse. This is a model. We place the field right at the peaks, so you get this broadening in both directions, if you like. This is the spectrum of the attosecond pulse that supports 70 attoseconds, assuming transform limited. And here is a calculation of what we would see in that case using one of these is classical, but you will see that there are circles and lines, dotted lines here, and one is a full quantum mechanical calculation. I can't remember which is which because there's almost no difference between the two. So F equals ma essentially gets it correctly. You can see all orders of chirp on the pulse, and this is for a chirp pulse, and I won't try to go through more of the measurement technique. Okay, so now I want to talk about a new measurement way of measuring pulse duration. So I said that you can modify the phase of this interferometer by using a second color field, and I want to go back and use that as a way of measuring. And I'm going to skip over just a few introductory slides and come directly to this. Okay, so this is the way we're going to do it. Here is the pulse that in our experiment creates an isolated attosecond pulse. You recognize it from before. It starts circular, goes linear, and back circular. This is polarization gating. And as I said, it can be made passively with wave plates, so it's relatively straightforward to do. So only near the linear part do we have an attosecond pulse being produced, a burst of radiation, which will be an attosecond pulse. I'll show you. You can think about the trajectories that lead to a given frequency. If you like in there, and there's an illustration, there's an assumed Gaussian here. Because the intensity is lower here, it's a little different moment of birth, a little different moment of recollision, but that's all right. This is only a sketch, and we just want to capture the fact that the trajectory is different in different intensities. But that's okay. That won't be important, but I want you to understand what's there. Now, I want to make a measurement. I want to be able to move the arms of the interferometer. So this is the beam we're going to use for moving the arms of the interferometer. It's a blue beam, second harmonic, phased with respect to the fundamental, coming in at an angle. And because of the angle, let's imagine the phase is just appropriate, that the second harmonic does not do very much to this trajectory, adds no phase whatsoever to this trajectory. Well, they're coming at an angle, so there will be a different phase up here, and so the arm of the interferometer will be changed differently, perhaps adding trajectory and adding energy, and therefore adding phase. It need be very little. And down here, again, for the same reason, the phase will be different, and we've drawn the case where the trajectory would be smaller. Really, all that counts is the phase. So the energy trajectory together would be smaller. So if you think about what happens here, we've created a beam moving at a slightly different angle than what it was before because of this phase. Remember, the phase of the electron is transferred to the light through the transition moment. So we've changed the distribution in the far field with this motion. And so here is such a measurement, spectrum, space, and you can see it at two different carrier envelope phase, one with respect to the other. And I don't know how well you can see it back there. Here you can see that it's mostly in the top, and there it's mostly in the bottom, and that's true everywhere you look. So we have moved the beam up, and we've moved the beam down with the second harmonic field. It's a weak second harmonic field. It's less than, but on the order of 10 to the minus 3 of intensity of the fundamental field. So here's isolated at 46 eV, a little window, and here it is at 79 eV, a small window. Phase delay between the fundamental and second harmonic. And this is experiment of what the phase delay is. We have it for every frequency. So as we delay the phase, there's a phase that moves down and changes. We change the phase continuously across the beam. This is a phase gate, and it can be put in a frog to reconstruct a spatial beam. So this is a reconstruction of this is our reconstructed spectrum in a frog-like algorithm. We actually use both frog algorithms, and the frog algorithm does almost perfectly. So at each frequency, therefore, we reconstruct a spatial profile, and here's the spatial profile coming from a frog-like algorithm, each frequency treated independently, and that's the spatial profile of the beam in the medium as it's being created. But there's a different time. If you look at the deflection as a function of phase, it's quite different in the time that, say, you get the maximum deflection for each frequency, and that's a way to tell you about the spectral phase of the beam. And so that also allows us to reconstruct the spectral phase. And so these are various ways to look at an attosecond pulse, since we know amplitude and phase in space and time. And I don't try to belabor what it looks like. We've always known that there's been spatial interferences in the beam and things like that, and different ways, slightly different divergences for different frequencies. But this is the first time we could look at it. So this is a measurement done in situ, and I've projected it far field, near field, and different ways of looking at it. I think this is an approach to a general way of measuring attosecond phenomena, because now that we have one pulse measured in the medium projected anywhere by spectral interferometry, we can look at any other phase-related pulse, either because of interaction with a dynamic medium or because of dispersion, linear dispersion, and other things that we've created on the beam. So I think this is a general method for, a new general method for measurement. I'd like to also say, you may also hear this because this is a thought that I think is also present in Israel. This kind of measurement is really an unusual measurement, but these strong field processes are really unusual processes. I think that it's general, and I like to think about it periodically. Strong field processes are hardly modified by a weak field. Here we use 10 to the minus 3 in intensity, and were the wavelength of the driving field longer, we could have used even much less intensity because the trajectories are longer, the accumulated phases are greater, and the modification to modify the phase by pi requires less second harmonic field. Yet the weak field can imprint an indelible mark, allowing us to make measurements with it. So I think this is a general concept for strong field processes. We've applied it to attosecond streaking, and here is attosecond, one attosecond pulse of those 4 pulses. We put an aperture, the input of the spectrograph, and we measure it directly. And there's an attosecond streaking pulse, and the fact that it streaks consistently up and down, up and down, up and down, up and down, is an indication that it's a single attosecond pulse. So we create single attosecond pulses, and we have similar data using other gating techniques. So I think we have now the tools for making and measuring attosecond pulses in this spectral range, but I think they can project all the way up to 500 eV with 1.8 micron radiation, and I think the measurement techniques will allow us to go there. And so it'll allow us to do coherent pump probe spectroscopy, I hope. I'd like to just end with that. I'm not the only person, I'd like to say this, I'm not the only person. This is the JazzLab group in Ottawa, and we take these every year in the front of the building that I showed you to start with. And so this is the group of people, and many of the people here contributed to the experiments, especially that I talked about today. I won't try to isolate those people, but thank you very much.